In this section, we will continue with another example of inference procedures, hypothesis testing. In this procedure, a hypothesis is proposed about the value of a population parameter. For example, as we use a lot, the mean or the standard deviation. This hypothesis is then tested for its validity based on the information obtained from a sample taken from the population. Now, in quality engineering, hypothesis testing is often used when there's a claim made about a population parameter. And we need to verify then the correctness of that claim. Now, if you remember in the last section, we had the example about turbidity of fabric softener. We used a sample of 4 turbidity measurements to calculate the mean of the sample, and then we constructed a 99% confidence interval about that value. And we said we could be 99% confident that the true population mean of the turbidity was within this interval. Now here, for hypothesis testing, we could verify a claim about the turbidity. For example, the claim that the manufacturer says his average turbidity is no more than, for example, 10 parts per million. So our learning objectives for this section are to describe how hypothesis testing is used to make inferences about population parameters. We want to be able to list the steps in performing a hypothesis test. And we will learn how to perform a hypothesis test concerning the mean of a normally distributed population with a known standard deviation. And finally, we have a very short section in order to explain the meaning of the so-called p-value when performing a hypothesis test. So, the basic procedure for hypothesis testing. We have 2 hypotheses that will be proposed. One is called the null hypothesis, and this we denote by H0. And the other is called the alternative hypothesis, denoted by H1. And generally, the null hypothesis and the alternative hypothesis are complementary to each other. And this means that if one is accepted, then the other is rejected, and vice versa. The claim made about the parameter is normally included in H1. So after the hypotheses have been set up, a sample is taken from the population in question, and the value of an appropriate test statistic is computed from the sample results. And for each testing situation, a suitable test statistic is chosen in such a way that it relates a sample estimator to the population parameter in question. So we did this before when we were looking for the mean, we used X bar. And in the case of hypothesis testing, of course, we will have a known distribution for our test statistic. Now, of course, there's a possibility of errors in our test. And so we have 2 definitions. We have a type 1 error, which will occur if our null hypothesis, H0, is declared false, when in fact it is true, and the type 2 error, which will occur if the null hypothesis, or H0, is declared true, when in fact it is false. And these we show on the next slide. So let's draw this. The possible outcomes of our statistical test are that the test declares H0, our null hypothesis, true or not true. It's not very clear here. So the test declares H0 to be true or not true. But in reality, we could have the case that H0 is true or not true. So what we have here then, it's difficult to write on this. What we have here then is if the test declares H0 to be true, and it is true, then we're in the top quadrant and we have a good test. If the test declares HO to be not true, and it is indeed not true, then we also have performed a good test. However, there are 2 of our 4 events which lead to errors in conclusions. And as we showed on the previous page, these errors are designated as type 1 and type 2 errors. The type 1 error will occur when the null hypothesis H0 is declared not true, when in fact it is true. And a type 2 error will occur when the null hypothesis is declared true, when in fact it is not true. Now, the probability of a type 1 error is denoted by alpha. This is also called the level of significance. This, we can call it the producer's risk. In the context of quality management, could be the probability that a good production lot will be rejected, or that a properly performing process will be rejected. The probability, on the other hand, of a type 2 error is denoted by beta. And this is the consumer's risk, or again, in context of quality management, the probability of accepting a lot of poor quality, or allowing a process which is operating in an unsatisfactory manner to continue to process. And the quantity 1 minus beta is called the power of the test. So as an example, I have a picture here of some medicine. The U.S. Food and Drug Administration, or the FDA, they need to approve new medicines. And when performing a hypothesis test to test the new medicine, which would be the alternative, the alpha level then is set by the FDA. The alpha is the amount of error that the government can tolerate to reject the null hypothesis and accept the new medicine, the alternative hypothesis. And alpha is set then to assume a certain small approved error. And what this means is that alpha is limiting the false positives, which means that they're limiting the probability to reject the null hypothesis and accept the new drug, even though the new drug has no effect. Now, if there's a type 2 error, then the FDA would approve the new drug, but there's no effect. In this example from the FDA, there's a risk of a false negative, meaning that the test declares the null hypothesis true, although the new drug works well, does not have an effect on the consumer, other than that they're not privy to the new drug until more tests are performed.